Hello and welcome to another NGen Math 6 lesson by eMath Instruction. My name is Kirk Weiler and today we're going to be doing Unit 9, Lesson 3 on trapezoids and their areas. So there's a lot of figures in geometry that are important. All right, and one of the very important ones is what's known as a trapezoid. So we're going to talk about what a trapezoid is. We're going to try to sort of identify some trapezoids given a bunch of different pictures. And then we'll talk about how we can find their areas by basically breaking them into rectangles and right triangles. All right, so let's first talk about what a trapezoid is. Right? So four-sided figures in general in geometry are known as quadrilaterals. And hopefully you've heard sort of the word quad before. Quad is sort of shorthand for four. Just like tri is 3, quad is 4, quint is 5, etc., etc. So a quadrilateral is just like any figure that has four sides. You know, that could be a rectangle, a square, a trapezoid, just a random four-sided figure. There are many special types of quadrilaterals. One is the trapezoid. So what is a trapezoid? Right, a trapezoid is any four-sided figure, aka a quadrilateral, with at least, and that's critical, at least one pair of opposite sides that are parallel. Now, since there's only four sides in a trapezoid, right, that means that you could have one pair of parallel sides or two pairs of parallel sides, and those would both be trapezoids. So let's see if we can identify a trapezoid in exercise number 1. Let's take a look. Circle all figures below that appear to fit the definition of what a trapezoid is above. Mark the sides you believe are parallel with arrows, and I'll talk to you about how you can do that. Now remember, when we talk about parallel sides, what we mean is if you took two sides and you extended them forever in both directions so that they were lines instead of line segments, would they intersect? And let's take a look at letter A together, all right? Let's take a look at this side and this side, those two opposite sides, right? If I extended those sides forever, right, like this, then eventually they'd intersect, all right? So those two sides, this side and this side, aren't parallel to each other. On the other hand, let me get rid of that. If I, extended this side and this side forever, well then no matter how far out they go in either direction, those two lines are never going to meet. In other words, that top side and that bottom side are parallel. And the way that we show that in geometry is by drawing two little arrows that sort of, if you will, point in the same direction. That's what parallelism really means. Pointing in the same direction. Those are horrible looking arrows, but you get the picture. All right, so what I'd like you to do, and I'm going to circle this, that is an example of a trapezoid, all right, because it's got at least one pair of parallel sides. All right, what I'd like you to do is go through the remaining 5 figures, do the eye test. Are there parallel sides? Are there not? If you think that they are parallel, mark them with, arrows that go in the same direction, and then let's talk about it. Pause the video now and see what you can do. All right, well this nice four-sided figure has absolutely no pairs of parallel sides. So it's a quadrilateral, but it certainly is not a trapezoid. Now this is kind of an interesting looking figure. Like letter A, it is a trapezoid because these two sides are parallel, right? So that's a trapezoid. Now let's talk about letter D. This one's interesting because in this case we actually have two pairs of parallel sides. These two are parallel again, and these two are also parallel. Now, oftentimes when you mark a second pair of parallel sides, what you'll do is you'll do it with a double arrow. And that just helps you identify which sides are parallel. So this side's parallel to this one, and this side's parallel to that one. So that's also a trapezoid, all right? Now this thing you might look at and go, well, that's a rectangle, so it's not a trapezoid. Well, that would be as weird as saying that that animal is not a mammal because it's a dog. Right? So there's subcategories of figures. Quadrilateral is the biggest category, four-sided figures, in terms of four-sided figures. Then you've got trapezoids, and underneath those you have things like parallelograms and rectangles and squares and rhombuses and all sorts of figures. So yeah, a rectangle is still a trapezoid because just like in letter D, these two sides are parallel and these two sides are parallel. The fact that it also has right angles and a bunch of things like that is kind of irrelevant. And our final figure, letter F, which is an important figure in geometry, it's what's known as a kite, Surprise! Kites are actually figures in geometry, but that thing again is not a trapezoid because that side is most certainly not parallel to that one, and that one is not parallel to that one. Whoops, I do not want to circle that. That is not a trapezoid, Kirk. Let's cross it out. Side note, we always talk about opposite sides being parallel and not adjacent sides like this one and this one, because the whole point is adjacent sides intersect right there, so there's no way they can be parallel. Parallel lines are ones that will never intersect ever, no matter how long they're extended. So, hopefully we can recognize a trapezoid when we see one. The question is, how do we find the space inside of a trapezoid, i.e. the area of a trapezoid? So let's keep talking about that. Finding the area of a trapezoid almost always involves breaking it into component rectangles and right triangles. This is known as decomposing a figure. Now it's kind of a long word, decomposing a figure, but you've probably heard the word decomposing before, right? If you have a piece of garbage or, like a banana peel, it will decompose out in the wild, which means it breaks down into its component parts. That's what decomposing really means, breaking down into component parts. So when we decompose a figure, it means we take something like this trapezoid and we break it into simpler figures like rectangles and right triangles. So let's take a look at that in exercise number 2. A right trapezoid is shown below with dimensions given. Decompose this figure into a rectangle and a right triangle. All right, well that's actually pretty easy, but let's do it together, right? So what we do is we simply draw this line down here, all right? And that forms sort of, if you will, an inner rectangle. Now, it would be good to just recognize the fact that this rectangle, right, has side lengths of 4 and 7 centimeters. Rectangles, like all parallelograms, have opposite sides that are the same length. So that means that this length is also 7 centimeters. This length is also 4 centimeters. And by default, that leaves me with this length here being 3 centimeters. It's very important, right? Because eventually, we're going to have to find the area of this right triangle. And in order to do that, we need to know its base and its height. All right, so let's do that in letter B. Find the area of both and add to find the area of the trapezoid. So it's pretty simple, right? We actually did this in the last lesson a little bit, and even in the lesson before that on rectangles, which is, if I can figure out the space inside the rectangle and figure out the space inside the right triangle, then when I add them together, that's going to give me the space inside of the trapezoid. So why don't you pause the video now and figure out the area of the trapezoid. All right, now keep in mind for the rectangle, it's not 4 times 10, right? It's 4 times 7, right? The rectangle is 4 by 7, not 4 by 10. So the area of the rectangle, though, is still very, very simple, right? The area of any rectangle is simply its base times its height, or its length times its width, or however you want to say it, and then I put down the 10, even though I just emphasized that it was actually 7. So the area of the rectangle will be 28 square centimeters. Now the area of the triangle, of course, we have to include that factor of a 1/2, so that's going to be 1/2 times 4 times 3. All right, we could do 1/2 times 4 and get 2. 2 times 3 gives me 6 square centimeters. And now the area of the trapezoid has to be those two areas added together, which will be 34 square centimeters. And that's it. And that is really going to be our strategy, both in this lesson and the next lesson when we look at the areas of parallelograms. We're going to be breaking them down into component rectangles and right triangles, finding the area of each, because we know how to do that pretty well, and adding together to get the total area within the figure. It's pretty nice and not that hard. So let's keep working with this idea. Now, just like rectangles, we can certainly orient a trapezoid in the coordinate grid, which is oftentimes done in the real world. If you're trying to create some kind of figure and you want to think about it in terms of its area or its perimeter or anything, getting it into the coordinate grid is very, very helpful. So let's take a look at a trapezoid in the coordinate grid. Exercise number 3. Trapezoid ABCD has vertices at A, 2, 6, B, 9, -2, C, -7, -2, and D, -5, 6. Letter A, simple enough. Plot A, B, C, D on the grid provided and label its vertices. All right, we'll take a little bit of time. This is some excellent practice in terms of just plotting points in the coordinate grid. Plot them, then connect them with straight line segments so that you get trapezoid ABCD. All right, well, for me, I wanted to save us a little bit of time, so I just pre-plotted it Anyway, there we have it, right? Nice trapezoid. We've got side AD and side BC parallel to each other. These two sides obviously are not parallel to each other, so here we go. Now, letter B. Redraw ABCD below. Decompose it into 2 right triangles and 1 rectangle. Label all relevant lengths. All right, so you could actually maybe do some of this on the grid itself. I just always find it helpful once I've got the figure on the grid to move it off the grid and work with it there. So let's first just redraw the trapezoid, and it doesn't have to be perfect in any extent. All right, but you know, maybe just something like that. Let's label the sides, right? Yep. Now what we want to do is we want to decompose it into 2 right triangles and a rectangle. Pretty much every time we do that, we're going to do something like this. All right, there's my 1 right triangle. There's another right triangle. Okay, and now what I want to do is I want to label all relevant dimensions. Now, when we say that, what we really want is we want all the lengths that are going to allow us to calculate the 3 areas we need. The area of that right triangle, the area of that rectangle, and the area of that right triangle. So one thing that might be helpful is just figuring out the height. You know, in general, the height of all of these 3 figures is going to be the same, and we can simply count, right? We can just go from D down to the x-axis, that would be 6 units, and then we can go an additional 2 units down, so this height is going to be 8 units, and I'll throw it over here as well. Right, we're also going to need to know what the width of the rectangle is, so that's just the distance from point D to point A, and that's going to be 7 units. And again, you can either count or you can think, from D to the y-axis is 5 units, plus another 2 is 7, whatever. I'll put the 7 down here as well. Now, it's very easy now to kind of make a mistake in terms of this distance. In fact, when I was filling out my notes for this lesson, I made that mistake. So for that, it might actually be helpful to bring this line in here and again count, and we've got 4 plus another 3. That's going to give me 7 here, right? Likewise, this one might be a bit easier to see visually, but if I draw it in, that's going to be 2 units there. And now I have everything I need, right? Because for this right triangle, I know its base and its height. For this rectangle, I know its length and width, or however you want to think about it. And for this right triangle, again, I know its base and its height. So, in letter C, now we want to determine the area of trapezoid ABCD by finding the area of the 3 figures from B and summing. All right, I'd like you to pause the video now and try to do that. One thing I think is very helpful in these situations is labeling the figures. I'll oftentimes do that by doing something like this. I'll put a little 1 inside of one of them and I'll circle it just so I know it's different from the dimensions. Right? I don't want to be confused about the 1, 2, 3. So I'm going to label this right triangle as 1, the rectangle as 2, and this right triangle as 3. That way for me, I can really kind of concentrate on, all right, the area of this thing is this, the area of this one is this, and the area of this one is this, and then I can add them all together. Pause the video now and see if you can figure out the area of this overall figure. All right, let's go through it. So for figure 1, right, its area is going to be 1/2 times 2 times 8. Again, you can do that in many different ways. You can do 1/2 times 2 and just get 1, and then 1 times 8 and get 8. For figure 2, that's quite easy. That's my rectangle. That's just going to be 7 times 8, and that's going to give me 56. And finally, let me put maybe 3 over here so you can see it. There, the area is going to be 1/2 times 7 times 8. Maybe do 1/2 times 8 and get 4. 7 times 4 is 28. So now I simply have to add 56 and 28. I'll get the 8 in there in a second. 14 That'll give me 84, and I'll take my 84 and add 8 and get an area of 92. Now, the one thing that's a little bit tricky about the coordinate grid is, what are the units? Some math teachers will say you don't have to have any units at all, because there's no units up here. There's no inches, no centimeters, no feet, no miles, no whatever. So maybe you just put down 92. Other math teachers will insist that you write something down like this, 92 square units. I would even kind of like it if kids just put down 92 squares, right? Because literally what you're counting is you're counting how many of these things, right? How many of these squares lied inside of that figure. Whatever it is, ask your teacher about it. Find out what they would prefer you to put down in terms of the units. Again, for some teachers, 92 is just fine. Okay, let's work with one more trapezoid. All right, maybe work with one more trapezoid. There it is. So there's a special type of a trapezoid called an isosceles trapezoid, okay? And this is specifically a trapezoid where there's only one pair of parallel sides, all right? So it's not a parallelogram or a rectangle or anything like that. There's only one pair of parallel sides, and the two non-parallel sides are the same length, okay? So let's take a look at an isosceles trapezoid in exercise number 4. Isosceles trapezoid EFGH is shown below. Find its area and state with appropriate units. Show how you arrived at your answer. All right, so let's be very clear about this, right? So we've got this isosceles trapezoid, right? Side EF and side HG are parallel to each other. One of them's 12 inches long, one of them's 20 inches long. And then the height of the trapezoid is 7 inches. All right. Now we still want to do this exactly like we did before. We want to decompose it into 2 right triangles and a rectangle. All right, what I'd like you to do is I'd like you to play around with it. All right, I'd like you to decompose it into the right triangles and the rectangle. Then I'd like you to see if you can find the area of all 3 figures, add them together in order to find the area of the trapezoid. If you get stuck, obviously we're going to go through it, but I'd like you to take a shot at this on your own. All right, well, there's one challenging thing really about this problem. And once you see it, it's not so challenging anymore. All right, let me try to erase that and do a little bit of a better job. Let's put this, and maybe I'll draw this in solid, right? Giving me, again, figure 1, figure 2, figure 3, okay? Now, all right, what's definitely clear to me is that if this is 12, then this is 12, right? And that's that rectangle. So I'm gonna put 12 right here, draw some lines out. What I don't know is what this length is and what this length is. But what I do know is that the entire length is 20 inches, right? So if I take my 20 inches and I subtract off my 12 inches, that leaves me with 8 inches left, all right? Now, where do those 8 inches go? Well, because this is specifically an isosceles triangle, an isosceles trapezoid, what that means is that the distance over here and the distance over here have to be the same. They have to be the same length. So this length and this length have to be the same. Since we have a total of 8 inches to divide up amongst the 2 of them, then this must be 4 inches. That doesn't look like inch. Let's try it again. This must be 4 inches, and this must be 4 inches. All right, and that's really the key with isosceles trapezoids, is that when you sort of take this and subtract it from here, you're left over with the remaining amounts and it divides up evenly. And now I have everything I need. So let's go through it. Let's figure out the area of this figure, 1, the area of this one, 2, the area of that one, 3. So for figure 1, whoops, that's not what I want. For figure 1, we've got the area. It's a triangle, so that's going to be 1/2 times 4 times 7. Again, I'm going to just divide that 4 by 2 and get 2. And so that will be 14 square inches. Figure 2 is that rectangle, so that's just going to be 12 times 7. And that is 84. Yep. Square inches. You can always sort of do that on the side of your paper if you don't know it off the top of your head. And 3. Now, just for a moment, And this is only true for isosceles trapezoids, right? Figure 3 and figure 1 are identical right triangles. So you could go through and say it's 1/2 of 4 times 7 again, or you could just recognize the fact that its area must also be 14 square inches. All right, in which case now all I have to do is take my 84 square inches, add to it 14, that will give me 98 square inches, take my 98, add another 14, and that will give me 112 square inches. Likewise, you could also take the two 14s, add them together, get 28, take the 28, add it to the 84, and also get 112 square inches. But that's it. We just take our isosceles trapezoid, decompose it into a rectangle and two identical right triangles, add up the area, and we've got the entire space, two-dimensional space, that fits inside this figure. All right, let's wrap this thing up. So today we learned just simply what a trapezoid is, right? A four-sided figure, a quadrilateral, with at least one pair of parallel sides. We were then able to find the area within a trapezoid by carving it up in a process called decomposing into rectangles and right triangles. We then find the area of each one of those D figures, those simpler, smaller figures within the trapezoid, add it all up, and we have the area of the trapezoid. We're going to be doing something very similar in the next lesson when we look at the areas of parallelograms. For now, I just want to thank you for joining me for another NGen Math 6 lesson by eMath Instruction. My name is Kirk Weiler, and until next time, keep thinking and keep solving problems.